some of the common gas laws, but they are simple mathematical relationships between volume, temperature, pressure, and quantity of gas. This is Boyle's law, Charles' law, Gay-Lussac's law, and Dalton's law. So the first one we're going to look at is Boyle's law. Boyle's law is a pressure-volume relationship. So if you were to have a closed syringe, so you know the syringes, you can squirt water at people with them, with a plunger. Yeah, without the needle on it though.
Of course, I know that.
Okay. If you were to cover the end of have it like halfway open, plunger halfway down, cover the end, and you were to push the plunger in, so your volume is decreasing, what happens to the pressure inside? It increases, right? So pressure, when volume goes down, pressure goes up, so they're inversely related. So this is our equation that we can use, where K is a gas constant, and it's the same, which all the gases have a different gas constant, but they're the same for that gas. So they're inversely related. So if I multiply P over, we have this PV is equal to K. So if we have the same gas and we change the conditions of it, so let's say we have a certain pressure and volume before, and then we switch the pressure, and we want to find what the new volume is, we're going to use this. Since K doesn't change, we can set those two equal to each other. And P1, V1 would be like the initial pressure and volume is equal to the final pressure and volume. So this bottom equation is the one that we'll use more than those top two. So some examples of that. If the sample of oxygen has a volume of 150 milliliters when its pressure is 0.947 atm, what's the volume of the gas at a pressure, or what will be the volume of the gas be at a pressure of 0.987 atm if the temperature remains constant? Units. It doesn't matter what units we're in for pressure and volume for this equation, as long as pressure units are the same on both sides and volume units are the same on both sides. So our equation is P1 V1 equals P2 V2. So what would P1 be? 0.947. So our initial pressure is 0.947. What's our initial volume? And so P2, our final pressure is and do we know V2? No, we're going to solve for V2. We're looking for the new volume. So to solve this, you're going to divide by 0.987 on both sides. $143 what? Divide by 0.987 on both sides. So multiply those two together and divide by 0.987. And what's our units? Milliliters. 143.9 milliliters. Good. Questions on how to do that? Let's try that next one, the helium-filled balloon. Consists of 125 milliliters of gas at a pressure of 0.974 atm. What volume will the gas occupy at STP? So what's our initial pressure? 0.974. What's our initial volume? Yeah, again, we're looking for volume, but what's our final pressure? Right, STP means standard temperature and pressure. What's our standard pressure? 1 atm. And then we're looking for V2. 129. 1.75. Units? Milliliters. Now maybe for some reason, if they would have given us the pressure, our initial temperature in millimeters mercury, you're going to have to convert either the ATM to millimeters mercury or the millimeters mercury number into ATM, just because you need the pressure in the same units. Okay, next law. Charles' law is the volume temperature relationship. What happens to the volume of a gas when the temperature goes up? Volume increases also. Or think about if you have a balloon and you're outside with it and then you come inside in the air conditioning. What happens to the temperature is going down? What happens to the volume of the balloon? It goes down. It shrinks a little bit, right? Or if you put a balloon in the freezer. Or when we had the liquid nitrogen and I poured liquid nitrogen over it, the temperature went really low and the balloon really shrunk. So they're directly related. Gases expand when heated. All gases expand at the same rate, and it's related to the Kelvin temperature instead of the Celsius temperature. So for temperature, you do have to be in Kelvin. How do we change Celsius to Kelvin? Do you remember? You add 273. So you're going to take your Celsius temperature and add 273 to make it into Kelvin. So your temperature has to be in Kelvin. It varies directly. So we have this equation, V is equal to K is the gas constant times T. V over T is equal to K. So if we have varying situations, changing volume and temperature, we can set them equal to each other since K doesn't change. So V1 over T1, so V1 divided by T1 is equal to V2 divided by T2. Yes, I will give you the equations for the quiz Thursday, I'll give you the equations.
For the test?
And for the test, for this one, yes. A sample of neon gas occupies a volume of 752 milliliters at 25 degrees Celsius. So our equation is V1 over T1, V2 over T2. What volume will the gas occupy at 50 degrees Celsius if the pressure remains constant? When it says the pressure remains constant, that's good because pressure isn't involved in this equation, so we know we don't have to worry about pressure changing. So what's our initial volume? 752 over what's our initial temperature? 298. Why 298? You have to change it to Kelvin. To change the 25 degrees Celsius into Kelvin, you add 273 to it, and it's 298. We are looking for our new volume, so we're looking for V2. And what's our new temperature? 323? 273. Add 273. So what does V2 equal? You can cross multiply and divide here. 815.1. What's our units? Milliliters. Now does that make sense? If our temperature goes up, the volume should go up. So we got a larger volume, which makes sense. Did everyone get that 815? When they calculated it? Okay. Next one about the balloon. It's filled with oxygen gas, occupies a volume of 5.5 liters at 25 degrees Celsius. What volume will it occupy at 100 degrees Celsius? So what's our V1? 5.5. What's T1? And we're looking for V2, and we know T2. All right, so V2, and you cross multiply and divide. .88. And what's our units? Liters this time. Since 5.5 is in liters, our answer is going to be in liters. And that's fine. Pressure and volume, you don't have to worry about what units they are as long as they're the same on both sides. Temperature has to be in Kelvin. Okay. Gay-Lussac's law is a pressure-temperature relationship. So think about the tires on your car. When the temperature in the middle of winter, what happens to the pressure in your tires? It goes down. So the temperature goes down in the winter, the pressure in your tires goes down. So they are directly related also. So we'll have P over T is equal to K. Again, we have to be in Kelvin for temperature. So we can have this relationship between varying situations where P1 over T1 is equal to P2 over T2. So if we use that for this problem, did I skip one or is that good? Okay. So we have P1 over T1 is equal to P2 over T2. So if a gas in an aerosol can is at a pressure of 3 atm at 25 degrees Celsius, and the directions on the can warn the user not to keep the can in a place where the temperature exceeds 52 degrees Celsius, what would the gas pressure be at that temperature? So what's our first pressure? And our temperature? 25 degrees Celsius is about room temperature. That's why you'll see it a lot. We're looking for the new pressure, and our temperature would be, so what is our new pressure? 3.27? So the can must not be able to withstand that amount of pressure. It would explode past that point, so that's why they have those warnings on it. Right? No one's ever done that, thrown an aerosol can, heated it so much that the pressure inside gets too large and explodes. Nope.
Why? In this chemistry class, don't blow stuff up.
No, we don't blow stuff up in here.
Mythbusters that do it all the time.
The temperature within an automobile tire at the beginning of a long trip, not a log trip. A long trip is at 25 degrees Celsius, and at the conclusion of the trip, the tire has a pressure of 1.8 atm. What's the final Celsius temperature within the tire if its original pressure was 1.75? So what would be P1? 1.75. What's T1? Right. Our initial temperature at the beginning. Do we know P2? This time we do. We know it's 1.8. But we're looking for our T2. We want to know the final temperature of the gas in the tires. So what is T2? $306.5. What's our units? Kelvin. So does that answer the question? You can cross multiply and divide. So 298 times 1.8 divided by 1.75. Right. It says find the Celsius temperature. So we need to do one more thing. How would we change Kelvin back to Celsius? Subtract 273, right. And should get something higher than 25. 33.5 degrees Celsius. Right. So any answer that you get, it doesn't matter what units you are in if the problem doesn't specify. If the problem specifies like this, then you need to make sure you're in the correct units that it asks for. Okay, any questions so far? Okay, the combined gas law, we are going to combine those three laws that we just learned about and put them together into one law, one equation that we can use for any situation where you have changing conditions. So since Boyle's law was pressure times volume, Charles' law was volume divided by temperature, and Gay-Lussac's law was pressure divided by temperature, we can make this combined gas law here. And if we have changing conditions, we can have P1 times V1 over T1 is equal to P2 times V2 over T2. And we can use this as a combined gas law. Now, if we have, really, this is the only equation you'd have to remember. You wouldn't have to remember those three individual ones because, let's say, here, I'm going to rewrite this so that it's in this format. Let's say the problem tells us that volume remains constant. So if volume remains constant, that means V1 is equal to V2, right? So I could rewrite this, and I would have, instead of V2 here, that's also V1 because they're equal to each other. And what would happen if I took V1 divided by V1? They cancel each other out. So if they tell me that volume remains constant, I can just take out volume from that equation, and I'd be left with this relationship here. And that goes with any of the variables. If they tell me pressure is constant, I can get rid of pressure out of this equation, and I'm left with volume over temperature. So whatever variable would remain constant, you can just leave out of this equation. So there will be times that all three variables are changing, and we'll have to calculate that, but sometimes it's just two. So if we have a helium-filled balloon with a volume of 50 liters at 25 degrees Celsius and 1 atm, we're looking for the volume, and the pressure has changed and the temperature has changed. We are going to use the combined gas law. So what is P1? What is V1? I guess we should check. Do we have all the same units? Liters. We're looking for volume. We're going to have to change Celsius, but these are both in ATM, so we're fine. What's T1? 298. What's P2? And V2? We don't know that. Okay, we have V2 then. T2? So now we're going to have to solve for V2. So I would solve this side, find this number. You're going to multiply by the 283 then, and then divide by the 0.885. So you have to do a little bit of algebra to solve for V2. 57.9. And we'd be in liters. Anyone else get that? Yeah? Okay. Are you still cross multiplying? Okay. How I would do it, I would solve on this side. I'd solve the left side. And then multiply by 283 and then divide by 0.885. My calculator go? Oh, it's right there. Yeah, I mean, it looks like it's a reasonable answer since we started at 50 liters and we went up to 2 or 57. That looks reasonable. Yeah, that's what I got. So I solved the left side, so the left side is equal to 0.181 on the left. And then you have to multiply by 283. You get 51.28, but then you have to divide by 0.885 to get 57. Okay, is this the last one? I guess I don't know. Pressure required to reduce 60 milliliters of gas at standard conditions. So what does standard conditions mean? What's our pressure? 1 atm. STP means pressure is 1 atm and temperature is 0 degrees Celsius. So 273. So our P1 would be 1. V1 is 60 over T1 is 273. I'm going to write this here. Right here. 1 atm and 0 degrees Celsius. If it says standard conditions or STP, that's what they mean. So it equals, we're looking for P2. V2 is 10 and 298. So we're going to solve for P2. And I get 6.5. Good. So any questions on those laws? Okay. So your assignment is actually out of the book. Right, I'll write it up here. So we have, it's on page 895. And these are the numbers.